Hi everyone and welcome. Today we're tackling LeetCode problem number 1931, painting a grid with 3 different colors. It sounds artsy, but it's a really neat logic puzzle. We'll break it down step by step, so don't worry if it seems tricky at first. Let's get started. So here's the deal. We're given 2 numbers, and these define the size of a grid, rows by columns. Initially, every cell in this grid is white. Our job is to paint each cell using one of 3 colors: red, green, or blue. The catch? No 2 cells that are next to each other, either horizontally or vertically, can have the same color. And all cells must be painted. We need to find out how many different ways we can paint the grid following these rules. The answer can be huge, so we'll need to give it modulo 1,000,000,007. Let's walk through a quick example. Suppose our grid is tiny, equals 1, and also equals 1, so it's just a single cell. We have 3 color choices: red, green, or blue. So there are 3 ways to paint it. Easy enough. Now what if is 1 and is 2? That's a grid with 1 row and 2 columns. For the first cell, we have 3 choices, say red. Then for the second cell, it must be different from red, so we have 2 choices left: green or blue. This gives us 2 ways if the first was red. Same logic if the first was green, or if it was blue. So it's 3 choices for the first cell, times 2 choices for the second. That's 6 total ways. The example image shows this nicely too. Okay, how do we approach this? Our first instinct might be, well, let's just try every single possible way to paint the grid. But if the grid is, say, 5 by 5, that's 25 cells. Each can be one of 3 colors, so that's 3 raised to the power of 25. That number is astronomical. Way too slow. Whenever we see problems about counting ways, and a brute force approach is too slow, dynamic programming often comes to the rescue. The problem mentions that the number of rows is quite small, only up to 5. This is a big hint. It often means we can use a technique called state compression based on this small dimension. So let's try to build our solution column by column. Imagine we're painting the grid from left to right. When we decide how to color the cells in the current column, say column, the only thing that really matters from our past decisions is how we colored the immediately previous column, column -1. The colors further to the left don't directly affect our choices for column, as long as column -1 was valid. This kind of dependency on just the previous step is a hallmark of dynamic programming. Now, how do we describe the coloring of a single column? A column has cells. Each cell can be one of our 3 colors. Let's give these colors numbers. Say red is 0, green is 1, and blue is 2. If we have a column with cells, we can represent its entire coloring pattern as a single number. Think of it like a base 3 number. For instance, if is 3, and the colors from top to bottom are red, then green, then blue, or 0, 1, 2, we can convert this into a unique number. We could say it's like 0 times 3 to the power of 0, plus 1 times 3 to the power of 1, plus 2 times 3 to the power of 2. That calculation gives us 0 plus 3 plus 18, which is 21. So the number 21 can be a shorthand, or a representing that specific red, green, blue column pattern. Every unique coloring of a column gets its own unique mask number. Before we even think about adjacent columns, there's a rule within each column itself. No 2 vertically adjacent cells in the same column can have the same color. So if we traces 2 or more, a column colored red, red from top to bottom is not allowed. But red-green would be fine. So, our first step is to figure out all possible color patterns for a single column that satisfy this internal rule. We can generate all 3 M theoretical patterns and then filter out the ones that have, say, red directly above red. It turns out there are 3 times 2 to the power of -1 such valid patterns. For equals 5, the maximum, this is just 48 patterns. That's a small, manageable number of valid column states or to work with. Now for the dynamic programming part. Let's define dpmask as the number of ways we can successfully paint the grid up to the current column we are considering, such that this current column is painted according to the pattern mask. And of course, mask must be one of those internally valid patterns we just talked about. We'll start with the first column, figure out the dp values for it, and then use those to calculate the dp values for the second column, and so on, all the way up to the column. So how do we move from one column to the next? Let's say we've already calculated all the dp values for column -1. Now we want to find the dp value for a specific current underscore mask in column. The value new underscore dp, current underscore mask, will be the sum of dp, previous underscore mask values from the previous column, but only for those previous underscore masks that are with our current underscore mask. What does compatible mean? Well, two things. First, current underscore mask itself must be internally valid. No vertical color clashes. We already ensured this by only working with our pre-filtered list of valid masks. Second, and crucially, for every row the color in current underscore mask at row must be different from the color in previous underscore mask at that same row. This ensures no horizontal color clashes between column -1 and column. If they are compatible, we add the ways to form previous underscore mask to the ways to form current underscore mask. And we do this for all possible previous underscore masks that could lead to current underscore mask. Okay, let's put it all together into an algorithm. First, we generate all those internally valid masks, the patterns for a single column that don't have colors clashing vertically. Let's say we also store the actual list of colors for each mask number. Second, to speed things up, we can pre-compute a quote transitions map. For every valid previous underscore mask, this map will tell us which next underscore masks are compatible with it, meaning no horizontal clashes. Third, we initialize our DP state for the very first column. Since any internally valid mask can start the grid, DP mask is simply 1 for all our valid masks. This means there's one way to paint the first column with that mask. Fourth, we loop from the second column up to the column. In each step of this loop, we create a new underscore DP table, all set to zeros. Then, we look at each previous underscore mask from the DP table of the previous column. For each of these, we look up all the next underscore masks it can transition to using our pre-computed transitions map. For every such valid transition, we add the count from DP, previous underscore mask, to new underscore DP, next underscore mask. Remember to do this addition with modulo to keep the numbers in check. Once we've processed all previous underscore masks, this new underscore DP becomes our DP for the current column. Finally, after we've processed all columns, the total number of ways to paint the grid is the sum of all values in our final DP table, again, taking the sum modulo MOD. Alright, here's the Python code for this solution. I know, it's a bit of a chunk, but don't worry, we'll walk through the key parts nice and easy, explaining what each bit does in plain English. The main ideas are exactly what we just discussed. First up, we have a couple of helper functions. The one named getColorsFromMask takes a mask number and, which is here, and it gives back the actual list of colors for that column. For example, if the mask number is 21 and is 3, it would return a list like color 0, color 1, color 2. The isInternallyValid helper checks if a given list of colors for a column is okay by itself, meaning no color is directly above the same color. Then, in the main part, we loop through all possible numbers, from 0 up to 3, to the power of -1. For each number we get its color list. Check if it's internally valid, and if it is, we store the mask number and its color list. This gives us our internally valid masks. Next, we pre-compute those transitions. We have another helper, are masks compatible? This takes the color lists for two masks, one for a previous column and one for a current column. It checks if they can be placed side by side, meaning, for every row, the color in the first mask is different from the color in the second mask at that same row. Then, we build our transitions map. For every valid previous underscore mask, we iterate through all other valid next underscore masks. If they're compatible using our helper, we record that next underscore mask is a possible follow-up to previous underscore mask. And here's the heart of the dynamic programming. First, we set up DP for the very first column. Every internally valid mask can be used, so there's one way for each. D. P deducts equals 1. Then we loop -1 times, because we've already accounted for the first column, and we need to build up to columns. Inside this loop, we prepare a new underscore DP dictionary, initially all zeros. We then go through each previous underscore mask that had a non-zero count in our current DP table. For each of these, we find all the next underscore masks it can transition to from our pre-computed transitions map. We add the count associated with DP, previous underscore mask, to new underscore DP, next underscore mask, making sure to use the modulo operator to keep the sum from getting too big. After checking all previous underscore masks, new underscore DP holds the counts for the next column, so we update DP to be this new underscore DP. Finally, after the loop finishes, the total number of ways is just the sum of all counts in our final DP table, again, with a final modulo. So how efficient is this whole approach? Let's call the number of internally valid masks We found this is at most 48 when is 5. Generating these masks takes roughly 3 to the power of m times m operations, which is pretty quick. Pre-computing all the transitions between these masks takes about s_valid squared times m operations. For equals 5, this is around 48 squared times 5, which is about 11,000 operations, also very fast. The main DP loop runs times. Inside the loop we iterate through our valid masks and their pre-computed transitions. In the worst case, this part is roughly proportional to requits times s_valid squared. With up to 1,000 and as 48, this is about 1,000 times roughly 2,300, so around 2.3 million operations. That's well within typical time limits for competitive programming problems. For space, we store the transitions map, which could take up to Hessen mac and the DP table for Russo Swati Itimhus, which Poldave. So to sum it all up, when you see a grid problem where one dimension is very small, like being up to 5 here, think about state compression dynamic programming. The trick is to represent the state of that small dimension, in our case, a column's coloring, as a single number, A. It's often a good idea to pre-calculate all the valid individual states, our internally valid masks, and the valid transitions between them. This makes the main DP calculation much cleaner and faster. Then, you build up your solution step by step, like we did, column by column. And, of course, for problems asking for a count that can be very large, don't forget to use the modulo operation at each step where numbers are added together. Hope that breakdown made sense and helped you understand how to tackle this grid painting problem. If it was useful, feel free to hit that like button, subscribe for more LeetCode explanations, or drop a comment if you have any questions or thoughts. And hey, if you're feeling extra generous, there's always the Boba Fund to keep these tutorials coming. Keep practicing, keep coding, and I'll catch you in the next one.